Hello and welcome. In the last video, we have introduced complex numbers. In this video, we will learn algebra of complex numbers. The first is the addition of complex numbers. Suppose that we have two complex numbers, z1 equal to a plus ib and z2 equals to c plus id. To add these two complex numbers, we simply add the real components separately and the imaginary components separately. Therefore, z1 plus z2 will be equal to a plus c plus I times b plus d. Z1 plus Z2 will be equal to the sum of real components a plus c plus I times sum of imaginary components b plus d. For example, if Z1 is equal to 1 plus 3i and Z2 is equal to 2 minus 4i, the Z1 plus Z2 will be equal to 1 plus 2, which are the real components, plus I times 3 minus 4, which are the imaginary components, and this is equal to 3 minus I. Therefore, Z1 plus Z2 is equal to 3 minus I. Now, there are some properties of addition of complex numbers which we should remember. First is the closure law, which says that sum of two complex numbers is also a complex number. Sum of two complex numbers is also a complex number. This is called closure law. The next is commutative law of addition. That means when two complex numbers are added, the order in which they are added is not important. That means Z1 plus Z2 is equal to Z2 plus Z1. This is called commutative law of addition. The next is associative law of addition. That means when we add Z3 to the sum of Z1 plus Z2, this is equal to adding Z1 to the sum of Z2 plus Z3. This means that the addition of complex numbers follow associative law. The next is existence of identity, existence of additive identity. That means for every complex number there exists an additive identity which is given as 0 plus 0i equal to 0, such that z plus 0, the addition of complex number with the additive identity, gives the complex number itself. So the 0 is the additive identity of every complex number. And the last one is existence of additive inverse. This means that for every complex number z, there exists the additive inverse minus z. For every complex number, there exists additive inverse minus z, such that z plus minus of z is equal to 0. Such that z plus minus of z is equal to 0. Therefore, minus of z is the additive inverse of complex number z. The next one is subtraction of complex numbers. Suppose that we have two complex numbers, z1 equal to a plus ib and z2 equals to c plus id. To find the difference between them, we take the difference of real components and imaginary components separately. Therefore, z1 minus z2 will be equal to a minus c plus I times b minus d. Z1 minus Z2 will be equal to A plus C plus I times B minus D. For example, if we have Z1 equal to 1 plus 3i and Z2 equal to 2 minus 4i, then Z1 minus Z2 will be equal to difference of real components 1 minus 2 plus I times difference of imaginary components 3 minus minus of 4. This will be equal to 1 minus 1 plus 7i. Therefore, z1 minus z2 is equal to minus 1 plus 7i. The next one is the multiplication of complex numbers. Suppose that we have two complex numbers, z1 equal to a plus ib and z2 equals to c plus id. To multiply these two complex numbers, we multiply each term of Z1 to every term of Z2. Therefore, Z1 into Z2 is equal to A plus IB times C plus ID. This means that Z1 into Z2 is equal to the product of real components AC plus the product of imaginary components I square BD plus the product of real component of one to imaginary component of another, real component of one to imaginary component of another, and summing them. This is equal to I times AD plus BC. Now I square is minus 1. We know that I square is minus 1. Therefore, Z1 times Z2 is equal to AC minus BD plus I times AD plus BC. Z1 into Z2 is equal to the product of real components AC minus product of imaginary components BD plus I times product of imaginary and real components and sum of them, that is AD plus BC. For example, if we have Z1 equals to 1 plus 3i and Z2 equals to 2 minus 4i, then Z1 into Z2 is equal to 1 plus 3i times 2 minus 4i. This means that Z1 into Z2 is equal to product of real components 1 and 2, that is 1 into 2 plus minus product of imaginary components, that is 3 into minus of 4, this is 3 into minus of 4 plus I times product of 1 with real component of 1 with real component minus 4, I times minus 4 plus product of imaginary component of 1 to real component of another, that is 3 into 2. Therefore, Z1 into Z2 is equal to 1 into 2 minus 3 into minus of 4 plus I times 1 into minus of 4 plus 3 into 2. And if we calculate it, we will find that Z1 times Z2 is equal to 14 plus 2i. Therefore, the product of Z1 and Z2 is 14 plus 2i. In the previous video, we have given a statement that the product of complex number and its conjugate is equal to the square of modulus of the complex number. Now we can prove that statement. Suppose that the complex number is a plus ib, then its conjugate will be a minus ib. Conjugate z bar is a minus ib. Therefore, the product of z and z bar is equal to a plus ib times a minus ib. That means z into z bar is equal to a square, product of real number components a square plus product of imaginary components ib times minus of ib, this is equal to minus of I square b square plus I times ab minus ab. I times ab, this ab comes from multiplication of this, the second ab comes from multiplication of this. Therefore, I times AB minus AB. This term is 0. Therefore, Z into Z bar is equal to A square minus I square B square, and I square is minus 1. I square is minus 1. Therefore, minus of I square will be plus 1, and Z into Z bar is equal to A square plus B square. Z into Z bar is A square plus b square. Now a square plus b square is nothing but the modulus square of modulus of complex number z. Therefore, z into z bar is equal to modulus of square of modulus of complex number z. Therefore, the product of complex number and its complex conjugate is the square of its modulus. Now there are some properties of multiplication of complex numbers which we should learn. The first one is the closure law, which says that the product of two complex numbers is also a complex number. Next one is the commutative law, which says that when multiplying two complex numbers, their order of multiplication is not important. That means z1 times z2 is equal to z2 times z1. The next one is the associative law, which says that if we multiply z1 and z2 and multiply the result to z3, this will be equal to multiplying z1 to the product of z2 and z3. This is called the associative law. The next one is the distributive law, which says that if we multiply z1 to the sum of z2 and z3, this will be equal to multiplying z1 to individually z2 and z3 and summing them. That means z1 times z1 z2 plus z3, z1 times z2 plus z3 will be equal to z1 z2 plus z1 z3. This is called the distributive law. Then next one is the existence of multiplicative identity, which says that 1 plus 0I equal to 1 is the multiplicative identity of any complex number, such that when it is multiplied to any complex number, it results in the same complex number. That means z times multiplicative identity 1 results in the complex number z. And the last one is the existence of multiplicative inverse, which says that for every complex number z, equals to a plus ib, if z is non-zero, then there exists a multiplicative inverse of z, that is z inverse equal to 1 by z, such that z times z inverse equal to 1. For every complex number z, there exists a multiplicative inverse z inverse such that their product results in the number 1. Now we will find the multiplicative inverse of a complex number. Suppose that we have a complex number z equals to a plus ib, where at least one of a or b is non-zero. Then the inverse of z, z inverse equals to 1 by z. To obtain z inverse, we multiply numerator and denominator by the conjugate of z. Therefore, multiplying numerator and denominator by conjugate of z gives z inverse as z bar, that is conjugate of z divided by z times z bar. Now we know that z times z bar is square of modulus of z. Therefore, z inverse is z bar divided by square of modulus of z. Therefore, z inverse will be equal to z bar, which is equal to a minus ib, and square of modulus of z, which is equal to a square plus b square. So z inverse will be equal to a minus ib divided by a square plus b square. The last one is the division of complex numbers. Suppose that we have two complex numbers z1 and z2, and we want to find z1 by z2. To find z1 by z2, we multiply z1 by the inverse of z2. Therefore, z1 by z2 is equal to z1 times inverse of z2. Now we already know that the inverse of z2 is equal to conjugate of z2 divided by square of its modulus. Therefore, z1 by z2 will be equal to z1 times conjugate of z2 divided by modulus of square of modulus of z2. z1 by z2 is equal to z1 into z2 bar divided by square of modulus of z2. For example, if we have z1 equals to 4 plus I and z2 equals to 1 minus 2i. To obtain z1 by z2, we first calculate z2 inverse. z2 inverse is z2 bar that is conjugate of z2 divided by square of its modulus. Now z2 bar is 1 plus 2i, z2 bar is 1 plus 2i, and square of modulus of z2 is 1 square plus 2 square. Therefore z2 inverse is 1 plus 2i divided by 1 square plus 2 square. This is equal to 1 by 5 plus 2 by 5i. Therefore z2 inverse is 1 by 5 plus 2 by 5i. Therefore z1 by z2 will be equal to z1 times inverse of z2, that is 4 plus I times 1 by 5 plus 2 by 5i. Using the rules of multiplication, we can calculate this as z1 by z2 equals to 2 by 5 plus 9 by 5i. This is equal to, this is the value of z1 by z2. Today's next topic is powers of I. In this topic, we will find what happens when we raise I to the some integer powers. The first one we already know, that is I square is minus 1. Next is I cube, which can be written as I square times I. Now I square is minus 1, therefore I cube is simply equal to minus of I. The next is I to the power 4, which can be written as square of I square. Now I square is minus 1 and minus 1 square is 1. Therefore I to the power 4 is minus 1 square equal to 1. The next one is I to the power minus 1, which is 1 by I. Multiply numerator and denominator by I, we get I inverse as 1 by I times I by I. Now 1 into I is I, and I by times I square equal to minus 1. Therefore I inverse is minus of I. Next is I to the power minus 2, which can be written as 1 by I square. Now I square is minus 1, therefore I to the power minus 2 is simply minus 1. Next one is I to the power minus 3, which can be written as product of I to the power minus 2 and I to the power minus 1. I to the power minus 2 is minus 1 and I to the power minus 1 is minus I. Therefore I to the power minus 3 is minus 1 into minus I. This is equal to I. This is equal to I. Next one is I to the power minus 4, which can be written as a square of I to the power minus 2. Now I to the power minus 2, we already know that it is minus 1. Therefore I to the power minus 4 is square of minus 1 equal to 1. We can generalize them as follows. I to the power 4k is equal to 1. That means when I is raised to the power an integer which is the multiple of 4, its value is 1. Similarly, I to the power 4k plus 1 is I to the power 4k plus 2 is minus 1, and I to the power 4k plus 3 is minus I. Now we state some identities involving complex numbers which are easy to derive. These identities are similar to the identities involving real numbers, and hence their proof will not be given here. The first identity is z1 plus z2 square. This is equal to z1 square plus 2 times 2 into z1 times z2 plus z2 square. The next one is z1 minus z2 square, which is equal to z1 square minus 2 z1 z2 plus z2 square. The next is z1 plus z2 cube, which is equal to z1 cube plus 3 z1 z2 times z1 plus z2 plus z2 cube. Next one is z1 minus z2 cube, which is equal to z1 cube minus 3 z1 z2 times z1 minus z2 minus z2 cube. And the last one is z1 square minus z2 square. This is equal to z1 plus z2 times z1 minus z2. To summarize, in this video we have learned about the algebra of complex numbers, we have learned about the powers of I, we have learned about the identities involving complex numbers. In the next video we will learn about the polar representation of complex numbers.